In the last class, we obtained the wave equation in one dimensions for a vibrating string. This is second order partial derivative of u, that is the displacement with respect to time, that is equal to c square times the second order derivative of the displacement with respect to x. Here c square is given by t. T is the tension in the string, and rho is the mass per unit length of the string. Okay, so this is the equation of a wave. This is a very important equation, and we are going to solve this equation subject to the boundary conditions. These are the boundary conditions. Here, one end of the string is fixed, that is at x equal to 0. The string is fixed, so there will be no displacement, that is the displacement will be 0. And the other end at x equal to L is also fixed. That means at x equal to L, there will be no displacement also. And this is true for all times. Okay, so we are going to solve this wave equation subject to this boundary condition and also subject to the initial conditions which are given by these two terms. There is the initial displacement is given by f of x, and the initial velocity is given by g of x. Here, f of x means different points on the string can have different displacements. Here, g of x means different points on the string can have different values of initial velocity. So we are going to solve the wave equation subject to the boundary conditions and the initial conditions. That is, the solution which we are going to obtain, it should satisfy the boundary conditions and also the initial conditions. Okay, so let us start solving it. Okay, so solution to wave equation. We shall solve the one-dimensional wave equation satisfying the boundary and initial conditions in 3 steps, where we're going to solve it in 3 steps. What is the first step? In the first step, we are going to use the method of separating variables or product method. This is also called the product method. And how do we do that? We do that by setting the displacement u is equal to f times g. Okay, where f is a function of only x and g is a function of only time. And by setting u equal to f times g, we obtain from the given wave equation, we obtain 2 ordinary differential equations. Okay, so we start with the wave equation and then we substitute u equal to f times g, and from the given wave equation, which is a partial differential equation, we shall obtain 2 ordinary differential equations. One equation for f of x and the other equation for g of t. That is step 1. In step 2, what will we do? In step 2, we shall determine solutions of these 2 ordinary differential equations that satisfy the boundary conditions. That is, we are going to solve these 2 differential equations and then we are going to put the boundary conditions. In step 3, what are we going to do? In step 3, finally, we are going to use the method of Fourier series and we shall compose the solutions that we obtained in step 2. I repeat, finally, using Fourier series, we are going to compose the solutions again in step 2 to obtain a solution of the wave equation satisfying the boundary as well as the initial conditions. That is, after step 3, we are going to find the final solution of our model of the vibrating string. So let us adopt these 3 steps and start solving. So step number 1, we are going to obtain 2 ordinary differential equations from the given wave equation. This is a wave equation in 1 dimension, so we are going to obtain 2 ordinary differential equations. If this wave equation were in 3 dimensions, then we shall obtain 4 ordinary differential equations. As we are considering only 1-dimensional wave equation, we shall obtain 2 ordinary differential equations. So in the method of separating variables or the product method, we determine solutions of the wave equation, and the wave equation is given by equation number 1, and we are going to determine solutions of the form u of xt is equal to f times g, which are a product of two functions, each depending only on one of the variables x and t. So differentiating equation number 2, we get the second order partial derivative of u with respect to time would be f times second order ordinary derivative of g with respect to time, and similarly second order partial derivative of u with respect to x will be the second order ordinary derivative of f with respect to x times g. Here g is a function of only t, so when we are partially differentiating with respect to x, we can take g as a constant. Similarly, here f is a function of only x, and when we are differentiating partially with respect to t, this f can be considered as a constant, and that is what we have done here. So we calculate these two derivatives, and then we insert these two values in equation number 1, that is in the wave equation, and we shall obtain this equation. Okay, f times d2g by dt square equal to c square d2f by dx square times g. Now what do? We divide both sides by c square fg. So dividing both sides by c square fg, and simplifying, we get 1 by c square g d2g by dt square equal to 1 by f d2f by dx square. Okay, what is our purpose of dividing by c squared g, c square fg? C square fg is not going to divide or square. Why are we dividing by c square fg? Because we want to separate functions of x and functions of times. So we are going to separate functions of x and functions of time. So when we divide by c square fg, on the left hand side we get functions of only time, and on the right hand side we get functions of only x. Here c is a constant. Okay, c is a constant. So the variables are now separated. The left side depends only upon time t, and the right side depends only upon the variable x. Hence, both sides must be equal to a constant. Okay, I repeat, both sides must be equal to a constant, because if they were not constant, then changing only t would affect only the left hand side, and changing only x would affect only the right hand side, and that would leave the other side unaltered. Okay, so if I change only t, it will change only the left hand side while keeping the right hand side constant, and that is not possible because these two should be equal. Okay, so that means both of this left hand side and right hand side both should be equal to a constant, and let us call the constant as k. Okay, so 1 by c square g d2g by dt square equal to 1 by f d2f by dx square, and both sides should be equal to a constant, and let us call the constant k. Okay, this is fine. Okay, then from this equation we can obtain two differential equations. So multiplying by the denominators gives the two ordinary differential equations. So if I multiply k by f, and then bring k towards the left, I should get d2f by dx square minus kf equal to 0. Similarly, if I multiply k by c square g and then bring k towards the left, I should get d2g by dt square equal to c square k times g equal to 0. So these are equations 3 and 4. So starting with the wave equation, we have now obtained two ordinary differential equations which are labeled by equation number 3 and equation number 4. Here the separation constant k is still arbitrary. Okay, the separation constant k is still arbitrary. Okay, now we are going to find solutions of equations 3 and equations 4 which satisfy the boundary conditions. So there is step number 2. So solutions satisfying the boundary conditions. And what are the boundary conditions? The boundary conditions are that the one endpoint, that is at x equal to 0, is kept fixed so the displacement would be 0. The other endpoint at x equal to L is also kept fixed. So that means the displacement at the point x equal to L is also 0. This is true for all times. We now determine solutions f and g of equations 3 and 4. These are the two equations, equations 3 and 4. These are the two ordinary differential equations. So we now determine solutions f and g of equations 3 and 4 so that u equal to fg satisfies the boundary conditions that is given by equation number, it should be equation number 5. So it satisfies the boundary condition. This 6 should be equation number 5 because boundary conditions are given by equation number 5. That is u x equal to 0, t, you put x equal to 0 here. So this becomes f of 0, t remains unchanged. So gt equal to 0. Similarly, you use the second boundary condition, you put x equal to L. So ULT, this is equal to f of x equal to L, gt, this is equal to 0. This should also be true for all times. And we label these two equations by equation number 6. First, let us solve equation number 3. Okay, equation number 3. We first solve equation number 3. And what is equation number 3? Equation number 3 is this ordinary differential equation for f. That is the space dependent part. Okay. We first solve equation number 3. If g is equal to 0, so for example, in this, if g is equal to 0, then u will be always 0. This 3 horizontal lines mean identity. That means if g is equal to 0, that means u equal to f of g, this will always be 0, which is of no interest. That means when u equal to 0, that means the string is not vibrating. Okay, and which is of no interest because we want to study a vibrating string. Okay, when u equal to 0, u equal to fg equal to 0 means the string is at rest, it is not vibrating, and this is of no interest. Hence, g should not be equal to 0. And by equation number 6, from this equation number 6, this g should not be equal to 0. That means f of 0 should be equal to 0 and f of L should be equal to 0. Okay, so from equation number 6, we get two conditions. F of 0 should be equal to 0. F of L should be equal to 0. Now we shall show that k must be negative. Okay, first, for k equal to 0, the general solution of equation number 3 is f. So let us come to equation number 3. So if this k is equal to 0, if you put k equal to 0, what do we get? So let me write it down here. If this k is equal to 0, then we have this differential equation d2f by dx square, d2f by dx square, this is equal to 0. Okay, so if I integrate with respect to x once, what will I get? So if I integrate once, I should get the first derivative, df by dx, this should be equal to a. Okay, now if I integrate this again with respect to x, what will I get? F will be equal to a times x plus a constant b. Okay, so if k is equal to 0, see k is 0, the solution will be f equal to ax plus b. That is what I have written here. Let me show it to you again. Here. Okay, so if k is equal to 0, the general solution of equation 3 is f equal to ax plus b. Okay, and now if we use this boundary condition, when x equal to 0, it should be 0. When you put x equal to 0, f is 0. So if I use the first boundary condition, when x equal to 0, f is 0, that means b should be equal to 0. Okay, now when I put the second boundary condition, when x is equal to L, f should be 0. So we already know b is 0. Now when I put x equal to L, f should be 0. So let me write it down here to avoid any confusion. So if I use this first boundary condition, then this becomes 0 equal to ax plus b. And I have put x equal to 0 here. So this x is equal to 0. So this will be 0. So a times 0 will be 0 plus b. This implies this is equal to b. So I get 0 is equal to b. That means b is equal to 0. So f should be only ax. Okay, since b is 0. Now let us use the second boundary condition. The second boundary condition is when x is equal to L, f is 0. So this is 0 when x is equal to L. Okay, when x is equal to L, f is 0. A is a constant here, and L is a given number, not equal to 0. That means since L is not equal to 0, A should be equal to 0. This implies A should be equal to 0. Why is L not 0? L is the length of the string, and the length of the string is not 0. So that means the constant A should be 0. So if K is equal to 0, the solution is this. And if we use the boundary conditions, we get A equal to 0, B equal to 0. That means F should be equal to 0. Okay, that means F should be equal to 0. And if F is equal to 0, that means U should be equal to 0 for all values of T. And which is also of no interest, because if U is equal to 0 for all values of X and T, that means the string is at rest. The string is not vibrating. And this is of no interest. Okay, so this is of no interest. So K equal to 0, we are not interested in this particular case. Okay, so what remains are only two possibilities. Either K can be positive or K can be negative. So let us look at those two conditions again. Okay, so if K is positive, then let us write K equal to mu square, where mu is some constant. Okay, so for positive K, it can be written as some mu square, where mu is a constant. Mu can be positive or negative, because when you take the square of a positive number or a negative number, it is always a positive number. So mu can be positive or negative. So you can write K equal to mu square. Now, when you put K equal to mu square in equation number 3, so in this equation number 3, if I put K equal to mu square, it becomes a linear differential equation and the complementary functions. I repeat, when I put K equal to mu square, it becomes a linear homogeneous differential equation, and the complementary function is given by a simple expression, that is f equal to A e to the power mu x plus B e to the power minus mu x. The solution of this we learned in our earlier classes. So let me do it again. So if K is equal to mu square, this equation becomes d square minus mu square f equal to 0. How do you find the complementary function? We find the complementary function by substituting d equal to m. So we get m square minus mu square equal to 0. So this implies m equal to plus minus mu. So there are two possible solutions. M is equal to plus mu or m is equal to minus mu. And what are the two independent solutions? The two independent solutions are e to the power mu x and e to the power minus mu x. So these are the two independent solutions. So if I multiply this by a constant a and I multiply this by a constant b and I take their sum, this will be the general solution. This will be the complementary function. Okay. So this is what we have obtained here. So e to the power mu x multiplied by a constant a and e to the power minus mu x multiplied by another constant b. And then we use equation number 7. Equation number 7 is this condition. So when you put x equal to 0, f should be 0. So this is the solution. Now we use this condition. So when you put x equal to 0, this becomes e to the power 0. This becomes also e to the power 0, and e to the power 0 is 1. E to the power 0 is 1. So the right hand side becomes a plus b. The left hand side is 0. So 0 equal to a plus b. So a plus b equal to 0. That means b should be equal to minus a. Okay, that means b should be equal to minus a. So b should be equal to minus a. From the first condition here, we get b should be equal to minus a. That means this equation becomes, so let me show it to you again. So b is equal to minus a. That means this equation becomes a e to the power mu x minus a e to the power minus mu x. Since b is equal to minus a here, we have obtained this solution. Okay. Let me erase this tick mark. Okay. So the function f is equal to a e to the power mu x minus a e to the power minus mu x. Now at x equal to L, the function is equal to 0. Okay, at x equal to L, f is equal to 0. So when you put x equal to L, this should be equal to 0. F should be equal to 0. So when a e to the power mu L minus a e to the power minus mu L, this is equal to 0. Okay. Now I can take a common. From these two terms, I can take a common. From these two terms, I can take a common, that is e to the power mu L minus e to the power minus mu L equal to 0. But this term inside the bracket, it is what? It is nothing but twice sine hyperbolic mu L. This term inside the bracket is twice sine hyperbolic mu L. And this cannot be 0. This will be 0 only if mu is equal to 0. Okay. But since we have taken that k equal to mu square and k is a positive number, mu is not 0. I repeat, k is a positive number, mu is not 0. That means when mu is not 0, this is not 0. That means this term inside the bracket is not 0. That means a should be equal to 0. A should be equal to 0. If a is equal to 0, sin a like rahe, sin minus a like rahe. So if a equal to 0, then both of these terms are 0. Therefore, f is 0. So this gives f equal to 0. So when you take k positive, when you take k as a positive number, you still get the case where f is equal to 0. And when f is equal to 0, f is 0 already, what do you get? You get u equal to f times g, u equal to f times g, f is 0 already. This will be always 0 for all values of x and all values of time. This means the string is not vibrating. The string is at rest. And this is also not the case which we are interested in. We are not interested in this case. Okay. So k equal to 0, the string is at rest. K equal to positive, the string is again at rest. So for a vibrating string, the only possibility is that k should be negative. So for a vibrating string, the only possibility is that k should be negative. And since k is a negative, then I can write k as minus p square. Okay, k as minus p square, where p is some constant. P can be positive or negative. When we take p square, the answer will always be positive. Now I multiply it by minus, then I get k as a negative number. So k can be written as minus p square. Okay, so when I put k equal to minus p square in equation number 3, the equation becomes this equation: d2f by dx square plus p square f is equal to 0. Okay, so let me clear all drawings. So when k is negative, we get this equation, and this equation, again, this is a linear homogeneous differential equation. The complementary function is a general solution. So the general solution is very simple. The general solution is a cos px, p is this, b sin px. So this is the general solution, where a and b are arbitrary constants. Now we are going to determine the values of a by using boundary conditions. Okay, and what are the boundary conditions? The boundary conditions are that at I repeat, boundary conditions are that at x equal to 0, f is 0, and at x equal to L, f is equal to, f is equal to 0. Okay, I repeat, the boundary conditions are at x equal to 0, f is 0, and at x equal to L, f is 0. So first, let us use the first boundary condition. At x equal to 0, the function is 0. So when you put x equal to 0 here, what do you get? Cos 0. And what is the value of cos 0? Cos 0 is 1. That means this is only a. And what is the value of sine 0? Sine 0 is 0. That means this term is absent. The second term is absent. Only the first term remains, and that is cos px becomes cos p times 0, and cos 0 is 1. So what remains is only a. So a is equal to 0. So using the first boundary condition, we get a is equal to 0. That means f of x should be equal to b sine px. F of x equal to b sine px. Now let us use the second boundary condition of equations given by equation 7. And what is the second boundary condition? The second boundary condition says that when you put x equal to L, f should be equal to 0. Now you put x equal to L here, that gives you b sine px, b sine pl. Instead of x, we replace L. So b sine pl is equal to 0. Now here we must take b not equal to 0, because here f is equal to b sine px. Karigumba b is 0 already, f will be 0. F 0 already, u will be 0. U will be 0 already. The string is not vibrating, and that is not what we are interested in. What we are interested in is a vibrating string. So b should not be equal to 0. That leaves us with the only option. And what is the option? Sine pl should be 0. Okay. So that the only option left is sine pl should be equal to 0. So sine theta equal to 0 means theta equal to n pi. So that means pl should be equal to n pi. Okay. Therefore, p should be equal to n pi by l. Okay. So from the second boundary condition, we find that p is given by n pi by l, where n is a positive integer. Okay, where n is a positive integer. Thus, we see that because of the second boundary condition, the constant p cannot take any arbitrary values. It should take only these possible values. These are the only possible values of p. Okay. So f of x equal to b sine px. So now we have solved p. We have solved for p. P is n pi by l. So let us substitute p equal to n pi by l here, and we get f of x equal to b sine n pi by l x from an error. And we can set v equal to 1 very easily. For simplicity, we can set b equal to 1, and we just obtain infinitely many solutions given by f of x equal to fn of x, where fnx is given by sine n pi x by l, where n goes from 1 to 3 and so on till infinity. Okay, here n n can take values 1, 2, 3 and so on. So for different values of n, we get different solutions. So how many solutions are possible? Infinitely many solutions are possible, and all these possible solutions are given by fnx equal to sine n pi by lx. So we have obtained the expression for f of x. Okay. So let me pause the recording here.